So our topic of discussion today is LC oscillator. LC oscillator. So what is a LC oscillator? When a capacitor, when a capacitor, when a capacitor is supplied with an AC current. Can we have class on logic gates, sir? అమ్మా మీరు ఆడిబుల్ మాట్లాడచ్చు. ఐ డోంట్ నో. యా డెఫినెట్లీ నాకు డెఫినెట్లీ అమ్మా, బట్ గివ్ మీ సమ్ టైమ్. డెఫినెట్లీ షూర్, గివ్ మీ సమ్ టైమ్, జస్ట్ గివ్ మీ సమ్ టైమ్. నాకు లాజిక్ గేట్స్ అని అంటే ఒక్క 1 వీక్ ఇవ్వండి టైం. నెక్స్ట్ వీక్ డెఫినెట్లీ విల్ పోస్ట్ ద క్లాస్ లాజిక్ గేట్స్. ఈజీ, వెరీ ఈజీ. సో మీరు ఇలా టాపిక్ అడుగుతుంటే నాకు కూడా ఎంకరేజింగ్ ఉంటుంది, లేకపోతే నాకే బోరింగ్ ఉంటుంది. ఓకే, నేను ఎలా సిలబస్ ప్రకారం వెళ్తున్నా. గుడ్ దట్ యు ఆస్క్డ్. లాజిక్ గేట్స్ డెఫినెట్లీ విల్ హ్యావ్. ఒక్క 1 వీక్ టైం ఇవ్వండి, నేను ఐ విల్ రికలెక్ట్ ఎవ్రీథింగ్ అండ్ కమ్యూనికేషన్ సిస్టమ్స్, బోత్ ద థింగ్స్. నెక్స్ట్ టాపిక్ అదే చేద్దాం అనుకుంటున్నా. వాట్ ఐ వాంట్ టు డూ ఇస్ కమ్యూనికేషన్ సిస్టమ్స్ అండ్ లాజిక్ గేట్స్. కమ్యూనికేషన్ సిస్టమ్స్ అనుకున్నాను, లాజిక్ గేట్స్ అయితే అనుకోలేదు. లాజిక్ గేట్స్ చేసిన తర్వాత కమ్యూనికేషన్ సిస్టమ్స్ చేసేస్తాను. దట్ విల్ బి ఫైన్, దట్ విల్ బి ఫర్ షూర్. ఒక్క 1 వీక్ టైం, జస్ట్ 1 వీక్ టైం, విల్ డూ దట్. సో దట్ ఈస్ ఆల్సో దేర్, దట్ విల్ డూ. Supplied with an AC current, it gets charged. With an AC current, it gets charged. It gets charged. Okay, so what happens when this charged capacitor is connected to an inductor? Is connected to an inductor. When this charged capacitor is connected to an inductor, current flows through the inductor. Current flows through the inductor. Through the inductor. Current flows through the inductor, giving rise to magnetic flux. Magnetic flux. So this is what you have to remember. When a capacitor is supplied with an AC, ante fully charged capacitor తీసుకున్నాం, and it is connected to a inductor. So how it is like this? This is the capacitor. It is connected to a inductor. Inductor means you assume it is a spring. That's it. Simply a spring. So it is connected to an inductor. Okay. Now this is a capacitor and it is connected to an inductor. This is capacitor is fully charged capacitor. Full charged capacitor. So what happens when you connect it to an inductor? The current flows through this. Okay. And the inductor will generate magnetic field. Inductor generates magnetic field. Okay, that's most important. So how does this inductor generates a magnetic field? It's like a solenoid kind of field. It will generate. It will generate a field like a solenoid. You can think of that. I told you, I think I discussed the solenoid, all these things in that chapter. I mean, moving charges and magnetism gives rise to magnetic flux. Now can I clear this once finished? Finished?
Yes, sir.
Okay, fine. Now, then what happens? It generates, hence an induced EMF. Induced EMF is produced in the circuit. Is produced in the circuit. Hence, the induced EMF is produced in the circuit. Due to this, the charge, or you can say energy on the capacitor decreases and an equivalent amount of energy amount of energy an equivalent amount of energy is stored in the inductor, is stored in the inductor in the form of magnetic field, in the form of magnetic field when the discharging of capacitor gets completed. So what happens? Whatever the capacitor it gets discharged, it will be stored in the inductor as magnetic field. That is what you have to understand. Okay. Can I clear? Hope I can. When the magnetic field is created, it develops an induced EMF. It develops an induced EMF linked with L. L means inductor. when the magnetic field is created, it develops an induced EMF linked with L, and it starts charging the capacitor. It starts charging the capacitor in opposite direction. That means recharging the capacitor in the opposite direction. In the opposite direction. Recharging the capacitor in the opposite direction. This is what happens. This process of charging and discharging of capacitor is repeated and energy taken from the source oscillates on C and L. Oscillates on C and L.
Noted, sir.
Okay, good. Now, as per the Kirchhoff's law, we can write the delta V on the capacitor is actually Q by C. And the inductor part, the delta V, that is nothing but the induced EMF. The induced EMF is minus L into di by dt. We can write like this. Okay, minus L into di by dt for the inductor, and I is also dq by dt. Okay, rate of flow of charge is current. So when you substitute these things, you will get delta Vc plus delta Vi is equal to 0 as per the Kirchhoff's laws. This we will get. This is the condition, because nothing external is coming. So it is Q by C minus L into di by dt is equal to 0. So we can substitute Q by C minus L into d square Q by dt square. So here if you find di by dt, what you get is double derivative is what you get. D square Q by dt square is what you get. That is equal to 0. Clear? And now you have this equation d square Q by dt square minus, so L will take common, will get Q by LC is equal to 0. This is a second order differential equation. But here we'll take a positive sign. There is one small thing I forgot to tell. We had to take the negative sign. I'll tell you why. Forgot to tell. It tells something. Minus L into di by dt, that's correct only. But when it comes to dq, we have to write plus. I will tell you why. Please write plus here. Forgot to tell. Written, noted. Here we have to write, this is a very specific equation. This tells something for us. So here I is equal to minus dq by dt represents when charge is decreasing on the capacitor, current is increasing in the circuit. Current is increasing in the circuit. This is what it says. When the charge is decreasing on the capacitor, current is increasing in the circuit. That's what it says. That's the reason this equation. Now, this is d square q by dt square plus q by LC is equal to 0. This is what you have. And now we compare this with an equation d square x by dt square plus omega square into, we'll write omega naught square into x is equal to 0. This is the equation for SHM. Equation for simple harmonic motion, you will get like this. Now, if you compare, your omega square is equal to 1 by LC, omega is equal to square root of 1 by LC, which is the angular frequency. Of course, at the resonance condition. This is called resonance condition, that is angular frequency, omega naught, that is square root of 1 by LC. So from this you can write f is equal to 1 by 2 pi square root of LC. This is oscillating frequency of the charge. Oscillating frequency of the charge. Oscillating frequency of the charge. This is an ideal situation. This is not realistic. That is one thing you had to remember. This is an ideal case. Otherwise, you will gain perpetual motion. This is ideal case. This is an ideal case. Sufficient. These are sufficient. Why they are not realistic is like a question they can ask. That can be one question. The next part is energy stored in an inductor. With that, we'll close today. Tomorrow we'll see transformers. With that, I think we can complete this chapter. Will be over. Transformers.
Thank you, sir.
Okay, right. Now we have another thing. We have now a question. A transmitter operates at 1 megahertz frequency, the oscillating circuit the oscillating circuit the oscillating circuit has a capacitance of has a capacitance has a capacitance of 200 picofarad. 200 picofarad. What is the inductance and capacitive reactance and capacitive reactance of the resonant circuit of the resonant circuit. Okay, this is the question. So it's simple. F is equal to 1 by 2 pi square root of LC we'll use. So you have to find the inductance. So F square, if you take 1 by 4 pi square into LC. So L you have to find, right? L is what you have to find. L is equal to 1 by 4 pi square F square C. So when you calculate L happens to be about 0.00013 Henry. 0.00013 Henry. So please plug in the values. ఈ values మీరు plug in చేసేస్తే మీకు వచ్చేస్తుంది. It's not a big thing. So L you get. So after getting L, you have to find XL. XL is equal to omega into L. Omega, it's given 2 pi f L. So this when you put, you will get the they asked capacitive reactance. Sorry, this is the inductive reactance. Capacitive reactance is what they ask. So the capacitive reactance XC is 1 by, of course you get this one also because this is a resonance circuit, right? So XC is 1 by omega C. Even if you put this or this, you should get the same value. So you will get XC is 1 by 2 pi FC 796.2. So it's about 796.2 ohms. This is what you get. 796.2 ohms. 1 by 2 pi. So XL is equal to XC. That's what happens here. So 1 by 2 pi FC. So when you put this, you will get this answer. Simple. Clear? Noted?
Yes, sir.
Okay, good. Now I'll clear this. Energy stored in the inductor. Energy stored in the inductor. Energy stored in the inductor is what we have to see. So how do we do this? So the current, when a current I flows in an inductor, of inductance L. Inductance L Henry. Okay. L Henry. It's measured in Henrys. Okay. So when it happens, we know that induced EMF is given by minus L. If we take the mod, so modulus of minus L into di by dt. So this equation you have to remember. Equation mata gurtundali. This is nothing but d phi by dt. That is rate of change of flux. That is EMF. Rate of change of magnetic flux. Rate of change of magnetic flux. Magnetic flux. So that produces inductance. Rate of change of magnetic flux. Now, can I clear? Now we'll write E is equal to L into di by dt. Now, E dt is equal to L di. This is actually epsilon. Okay, we can write E dt is equal to L di. Now we know power is instantaneous power is given by dw by dt. Work done, rate of change, rate at which power is the rate at which we do the work. So dw by dt, and we know dw is equal to p dt. And now p is nothing but I into v. So we know that. So that is E into I into dt. This is how we write. And now integrate dw. dw is equal to integral E I dt. So this is what we have. But what is we can write the further equations like E dt is L di. We can write E into dt is L di. So integral L I di. So E dt is E into dt. Of course, I should put like this. E I dt. E dt, E I dt is E into dt is L into I into di. We can write like this as E dt is equal to L di. So once you plug in that, L will be coming out. So the work done is L is out. So when you integrate, you get I square by 2 half Li square. So that's the work done. So this work done is stored as energy in the inductor. So U is half Li square. This is how I get normally. So there is one more thing I want to tell. This is a conservative type of work. Okay, conservative work. So even we actually speaking without change of the sign, we have to solve this, but it's okay, no problem. U is equal to Li square, half Li square. This is the energy stored in the inductor, or this is half into this is nothing but this is the energy stored in the inductor, and the energy stored, this is, let us write Ui. The energy stored in the capacitor is Q square by 2C. So for an LC oscillator, Q square by 2C is equal to half Li square. So this is a very important relation because UC is equal to UI. whatever the energy stored in the inductor is equal to the energy stored in the capacitor. So UC is equal to UI, Q square by 2C is equal to half L square, that is UI. This is the concept. So this is the concept. This is equal to UC, that is Q square by 2C. This is what you have to remember, this much. Clear, written. Clear, written.
Yes, sir.
Okay. Suppose an inductor and a capacitor are connected. Inductor and a capacitor are connected. Are connected in circuit. Connected in circuit. Total energy stored is U total is UC plus UI. Suppose this is like a circuit. అంటే మనం ఒక circuit కి capacitor and inductor LC circuit with an AC source like this. Now what is with the total energy stored with this? UC plus UI simply. So it is Q square by 2C plus half Li square. That's it. So this you have to remember, U total. This is what you have to remember. This is called electromagnetic energy. Electromagnetic energy. This is called electromagnetic energy. Sufficient. Tomorrow last part we'll see about this one. That is transformers. That will close thus. Next, I will work out the communication systems and the what is that? Electronics. We'll go to that definitely. First, I was thinking of feeling the communication systems. Okay, we'll close now. Tomorrow we'll see.
Thank you, sir.
Okay, Mara.